And now, equivalence theorem. Equivalence theorem is the most useful of this set of theorems and principles in this chapter because it will allow the formulation of the integral equations that we have to solve using numerical methods. In fact, the problem is that we have set the way to compute the fields due to some sources, to some electric and magnetic currents, but in free space. Remember that in chapter 1, at the end of chapter 1, we obtained the equations of the fields produced by some electric and magnetic electric currents, and by duality you know how to compute them for magnetic currents. But remember that the condition was that the space was homogeneous, and we assume free space with the electric constant epsilon 0 and magnetic constant mu 0, but it can be any medium with any epsilon and mu, assuming that it is constant. And it must be so, homogeneous space, because we use the convolution with Green's function, the impulse response, using linear system theory, in which the output of a system is the convolution of the impulse response with the input, which is valid for invariant systems, time invariant systems in time domain, or space invariant systems here. And a space invariant system here means homogeneous space. Okay? So for that reason, as a consequence of using the convolution with the Green's function, which is the impulse response, we are restricted to computation of electromagnetic fields due to some currents only in homogeneous space, usually free space, but can be any other medium. Okay, but in practice we have to solve problems in which space is not homogeneous. We have an antenna with some shape, we have an object that diffracts field. For example, a typical problem that will be we will address in chapter 4, we will address the problem of radar cross-section, which is the computations of the fields reflected by a radar target back to the radar. And it is just an important problem of fields diffracted by an object. But there are many applications of the computation of fields diffracted by an object, not only radar, but there are many more applications. For example, just the radiation patterns of a mobile phone antenna in a complex environment, including reflection with many objects or whatever. So we need to solve problems in which we have some object. Here is a volume. The object can be inhomogeneous, can have epsilon different than epsilon 0, mu different than mu 0, can have a conductivity. This can be inhomogeneous, so they can vary for different points in space inside the object. And outside the object, we have a free space outside. Now, and then we have some currents that are called impress sources. These impress sources are the sources that introduce power in the medium. So these impress sources radiate some fields or produce some fields if it is near field and not far field. And these fields are diffracted by the object. And overall, we have electric and magnetic fields that are different to those that would be produced by the impressed currents in free space. In fact, we define as incident fields here the fields produced by the impressed sources in free space. So, if we have free space, that is, if we replace our object with free space, and we have free space everywhere, the impressed currents produce some fields that are called incident fields. And we use superindex or subindex I from incident fields. Okay? So we have the same Maxwell's equations, but now we have the same Maxwell's equations with the same impressed currents, but now the fields are the incident fields because the medium is free space. Okay? In the original case, we have some object with some epsilon, some mu. So we have the epsilon of the object, the mu of the object, and the total fields E and H in presence of the object. Okay? So we can very easily compute the incident fields using the conventional formulas of convolution of the sources, that are the impressed currents, with the Green's function. Okay, so these are the convolution of the Green's function with the impressed currents. Okay? But we need to solve this. We need to solve the radiation of the impressed currents in presence of the object and obtain this E and H here. How can we do that? Okay, first we subtract the Maxwell's equations with the object minus the Maxwell's equations without the object. Since the sources are the same in both, they cancel out. Okay? And what we get? At the left hand side we get E minus EI here, H minus HI here, and in the right hand side we get the terms of the original Maxwell's equations minus the terms of the Maxwell's equations in free space. So we copy these equations here. These are the equations that we obtained before. These are the same equations that we obtained in the previous slide. And now we define, very important, the scatter fields. We define the scatter fields here as the difference between the fields with the object minus the incident fields that are the fields without the object. That is, these scatter fields take into account the effect of the object, because they are the fields with the object minus the fields without the object. So these are the perturbation introduced by the object in the incident field that are the fields without the object. We add the perturbation introduced by the object, and then we get the total fields. For that reason, the fields with the object are often called the total fields, because from this definition of a scatter field we can clearly see that the total fields are the fields without the object, or incident fields without the object, plus the scatter fields, which are the perturbation introduced by the object. Okay? So we use this definition and we replace this definition in our subtraction of Maxwell's equations, and what we get is this. We get all this. And here we observe that we have on the left hand side the curl of the scatter fields, and at the right hand side we have some term plus the time derivative of mu h or epsilon e, which are in fact the first is a Faraday equation and the second is a Per-Maxwell equation, in which this term here and this play the role of sources, and we define, in comparing with a conventional Faraday law in the first case, we define the first term as a magnetic current, and obviously the second term is the usual term in Faraday equation. And the same in Per-Maxwell equation, we define the first term as equivalent electric current, and the second term is the conventional time derivative of epsilon sub 0 e, that is the time derivative of the displacement vector d. Okay? So what we got are a pair of Maxwell's equations in which our fields are the scatter fields and the sources are the equivalent currents defined as these terms. This term here and this are defined as the equivalent current. More about this in the next slide. So, in the equations that we got, the sources are the equivalent currents, the fields are the scatter fields, but very, very important, look at the dielectric constant and the magnetic constant that we get. They are epsilon 0 and mu 0. They are the constants of free space. So, in the new problem, we have the equivalent currents producing the scatter fields, but very important, in free space. And remember that we know how to compute fields in free space as the convolution of the Green's function with the current, okay? So, we had a problem in which we have some impressed currents and some inhomogeneous object that produce the currents together with the object produce some electric and magnetic fields, and we can split this problem in two. It is computed as the radiation of some equivalent currents defined in this way, and this definition comes from the term that we got in the previous slide, okay? Remember that the definition that we have made for the equivalent currents comes from these terms that we got here, and we made this term equal to some equivalent current, okay? So this is the definition of the equivalent current. These equivalent currents here produce the scatter fields in free space, very important. And then we have to add, because remember that we got this, so the total field is the incident field plus the scatter field, we have to add the incident field. And the incident field is the field produced by the impedance currents in free space by definition. So we have now two free space problems, and we just have to add okay, we just have to add the total field equal to the scatter field due to the equivalent currents plus the incident field due to the impressed currents in free space, okay? So we have reduced a difficult problem involving an inhomogeneous medium. This problem we have an inhomogeneous medium here and some sources that are producing some fields, and we have simplified it as the addition of two problems. We have to add these two problems here. The addition of two problems involving free space in both. The first problem is the radiation of the impressed currents in free space that produces the incident fields, and the second problem is the radiation of the equivalent problems in free space and produces the scatter fields. And again, we compute the total fields as the addition of the incident fields plus the scatter fields. But have we simplified the solution? Well, now we work only with free space radiation, which is what we know how to compute, but the problem is not simple, because the equivalent currents depend on the electric and magnetic fields that we want to compute. So we want to compute these electric and magnetic fields, and in order to compute it, we have to sum the incident field, which is easy to compute. The incident field is easy to calculate because it's like just the radiation of the impressed currents in free space. Okay, this is easy. But we have to sum the scatter field. The scatter field is not so easy because it's the radiation of some currents that depend on the fields that we want to compute. So these currents, these equivalent currents, sorry, here, these equivalent currents here are just are not known. They depend on the unknown. So these are not known. But what we can do is to set an integral equation. So let us summarize what we have. The total field is the summation of the incident field plus the scatter field. The incident field is known because it's very easy to compute. It's just the radiation of the impressed currents in free space, okay? So no problem with this. This is just, as I said before, the convolution of the Green's function with the impressed currents. No problem with this. This is known. No problem. And then we have to add the scatter field. The scatter field is the radiation of the equivalent currents. So it's the convolution of the Green's function times the equivalent currents for the electric current and the convolution of the Green's function with the magnetic equivalent current. And we replace the equivalent currents by its value. To simplify, we assume a non-magnetic problem in which mu is the mu of free space vacuum, and then the magnetic equivalent current becomes equal to 0 because it has a factor mu minus mu 0. Both are equal, so the subtraction is 0. So the magnetic current cancels out. But it's just a particular case, a very common case, the case of a non-magnetic medium. But just to simplify the formula, I assume this. And then we replace the equivalent current here. The equivalent current here is replaced by its value. So we substitute this here, and we get this. The convolution of the Green's function with some factor that depends on the electric field. Essentially, the convolution of the Green's function with the electric field times a factor that depends on the object. This includes the information about the object. And now we have what's called an integral equation. We have an integral equation because we have the unknown inside the unknown in the left hand side and also on the right hand side. Then we have the convolution of the unknown with some Green's function that is known, and a factor that this factor includes the information of the object, as I said before. This is known, plus a term that is also known. So everything is known here except the electric field E, which is the unknown of the problem. So we will discretize this equation with numerical methods, and M is numerical methods. We will discretize this equation with numerical methods and obtain the electrical field, which is the unknown. In fact, we will use a method called method of moments to discretize this equation and get a linear system of equations in which the unknown are samples of the electric field. So equivalence theorem has allowed us the formulation of an equation for the electric field in a difficult problem. The problem was difficult because remember that our original problem was difficult because it was the radiation of some currents, impressed currents, in the presence of an inhomogeneous object, and we only knew how to compute radiation of currents in free space, but not in presence of an object. Now we have learned that we can set an integral equation that includes the information of the object and the Green's function, and the unknown is the electric field in the presence of the object. This formulation of equivalence theorem is called volume equivalence theorem because volume equivalence, because the formulation is for equivalent currents that are defined inside a volume, the equivalent currents depend on R, depend on the position. So the equivalent currents here depend on R prime inside the integral. This is the relation with respect to V prime. And it is a volume integral. It's called volume equivalence theorem that leads to a volume integral equation. And I repeat, it's volume because we define everything within the volume of the object. We define the epsilon, it can be an inhomogeneous object, and we define the epsilon and the mu as variables inside the volume of the object. We get equivalent currents that are defined on the volume of the object, and we compute the convolution integrating on the volume of the object. But there is another formulation of equivalence theorem that is called surface equivalence theorem, that it is in fact more useful for numerical methods because it involves the definition of the object in a surface. It involves only surface integrals and not volume integrals, which are much faster to compute, and therefore the numerical methods that we obtain from surface equivalence theorem are much more efficient than numerical methods obtained from volume equivalence theorem. So surface equivalence theorem formulation will be the most important for us. And in fact, this formulation is related to Huygen's principle that you already know, that says that each point on a primary wavefront can be considered to be a new source of a secondary spherical wave, and a secondary wavefront can be constructed as the envelope of these secondary waves. Well, this is known for you and is related, as you will see later, to surface equivalence theorem. In fact, surface equivalence theorem is based on uniqueness. It's based on uniqueness theorem. The equivalence theorem based on uniqueness theorem altogether is due to Shelkunov, that also made important developments on antennas. And this theorem is very old, 1936, as most of the theory in electromagnetics is old. And it's based on uniqueness. And I remind you about uniqueness. It says that a field in an homogeneous, very important that the region must be homogeneous. The field in an homogeneous volume or region V is uniquely specified by the sources within the region, this, plus the tangential components of the electric field over the boundary, that is tangential components of electric field, or tangent components of magnetic field, or the former in part of the boundary and the other and the later in the rest of the boundary. So, and as I said before, the object must be homogeneous, that is, epsilon, mu, and conductivity must be constant within the object. The object is defined by volume V and enclosed by surface S. So, in our case, we are very often interested in the fields radiated by antennas or diffracted by objects. As remember the field diffracted by an object in volume equivalence theorem. So normally we are interested in computing the fields in volume V that it is outside the object. Okay? So volume V is Fourier space that is homogeneous, and it is enclosed by surface S inside and by infinity outside. Okay? So volume V is this, and it is in the outside of surface S, and surface S encloses the object. So, as I said before, we apply uniqueness to volume V that is outside surface S and enclosed by infinity. Okay, then, In order to apply uniqueness, we define an equivalent problem. In the equivalent problem, we remove the object. So the object, epsilon 1, mu 1, the object is removed. Okay? And we replace the object by free space. Why by free space? Because we want to have free space everywhere. Because remember, the same as in volume equivalence theorem, remember that we know how to compute the fields due to or produced by currents in free space, but not in the presence of an object. To take into account the object, we will set an integral equation, the same as we did in volume equivalence theorem. So we need to have free space everywhere, and for that reason we replace our object with free space. Now we set in the inside of the object the total the fields, electrical magnetic field, equal to 0. It is not necessarily that they are 0, they can be anything else, but it is much easier, much simpler if we set the fields to 0. Okay? And we want this equivalent problem to be a correct problem, to be a problem that agrees with Maxwell's equations. So, this equivalent problem has, in volume V outside surface S, has the same fields as the original problem. The same fields of the original problem agree with Maxwell's equation. So, they are correct. Inside surface S, we have set the fields equal to 0. And this is again correct, because fields equal to 0 and sources equal to 0 agree with Maxwell's equations in which everything is 0. So here the fields and the sources everywhere agree with Maxwell's equations, except we need something else. Here we have a discontinuity, and at the surface S we have a discontinuity between the original fields outside S and 0 inside S. So in order to support this discontinuity, we need a current that is called equivalent current and agrees with boundary condition. These equivalent currents are the currents that agree with boundary condition and support the discontinuity between the original fields in the outside and the 0 fields in the inside. So, as it's explained here, we have just replaced the object with 0 fields and free space inside S, and define and set some equivalent currents, surface equivalent currents that flow along surface S and have the exact value to agree with the boundary condition. And according to uniqueness theorem, in volume B that is the outside of S, we have the same sources as in the original problem, and we have the same tangential components of electric and magnetic field in surface S as in the original problem. The tangent components of electric and magnetic field are the same as in the original problem, because the fields are, in fact, in the outside of S, the fields are the same. And we have defined these equivalent currents that support the discontinuity and make this possible to have the step between the original fields outside and the 0 fields inside. So, according to uniqueness theorem, the fields in the outside are uniquely defined, and since they are unique, there must be the same fields in the original problem and in the equivalent problem. So, to summarize, we had original problem with some impressed sources. They can be inside S or outside S, or in both inside and outside S. we have some object that together with the sources produces some fields in the free space that is outside S. And we can have the same fields outside S as the fields due to the impressed currents outside S, only the impressed currents outside S, because the impressed currents inside S have been removed. Remember that when we remove everything inside S, we remove everything and substituted it by zero fields and free space, we remove the fields, the object, but also the impressed currents inside S. So in the equivalent problem we have only the sources outside S, original sources, impressed currents, but also the equivalent currents along surface S. And by superposition, since we have two sets of sources, we have the original sources or impressed sources outside S and the equivalent currents along S, according to superposition, we split the total fields in the summation of the fields due to impressed currents in free space because we have free space everywhere now. So all the currents radiate in free space. So by superposition we have the fields due to the impressed currents in free space, but only the impressed currents in volume B outside surface S, and these are called the incident fields. These are called the incident fields, the same as we define in volume equivalence theorem. The fields due to the impressed currents in free space are the incident fields. And then we have the fields due to the equivalent currents. And the fields due to the equivalent currents are the scattered fields because they are the difference between the total fields and the incident fields. So, the same as in volume equivalence theorem, we define the scattered fields as the difference between the total fields and incident fields. Okay? And scattered fields are due by superposition. Scattered fields are due to the equivalent currents. In this case, the same, the surface equivalence currents. But the same as in volume equivalence, we have total fields equal to incident fields due to impressed currents in free space plus scattered fields due to equivalent currents in free space. The only difference with the volume equivalence theorem is that now the equivalent currents are not defined in the volume inside the surface S, but now equivalent currents are defined along surface S. And it is very important to have surface equivalent currents instead of volume equivalent currents, because when we compute the radiation of these currents, we will have a surface integral instead of a volume integral. And this will be computationally much cheaper to compute the surface integral than the volume integral, which is much more expensive. So, now it seems that everything is simple because both the impressed currents and the equivalent currents radiate in free space, but again, the same as in volume equivalence theorem, the equivalent currents depend on the total fields. The equivalent currents depends on the total fields that are the fields that we want to compute. So, again, we will need to set an integral equation in which the unknown will be the equivalent currents. We will do this in a later slide. Two comments. The equivalent problem does not necessarily need zero fields inside S. We can also solve the equivalent problem with non-zero fields inside S if they agree with Maxwell's equations. But anyway, forget about this because in practice we will always we will always define zero fields inside S, because it is much easier for the formulation of numerical methods. And also, if we have a dielectric object, normally we need to compute the fields outside the object, but also inside the object. And in this case, we have to make two formulations of surface equivalence theorem. One formulation to compute the fields outside S, which is I have already shown you, and also a similar formulation to compute the fields inside S. And now we define zero fields outside and non-zero fields, the original fields inside S, and we make a similar formulation to obtain the fields inside S. In the case the object is dielectric, we use both formulations simultaneously to set the system of integral equations. But this is more advanced, and we will keep here, in this course we will keep here to the simpler case in which we have a perfectly conducting object, and we define, and in a perfectly conducting object we already know that the fields are zero inside the object, so we only need to compute the fields outside the object, and in this case we only have to formulate surface equivalence theorem outside the object, because it is the only place where we need to compute the fields. Okay? So remember, in the case of dielectric objects, we also need to formulate the surface equivalence theorem inside S, and we need both formulations altogether to set the system of integral equations. But we will not do this in this course because it's much complicated, and we will keep here to the simplest case. And now a numerical test. I said that in the equivalent problem we have the summation of the incident fields due to the impressed currents plus the scattered fields due to the equivalent currents, and we have zero fields inside S. It is quite difficult to believe this about zero fields inside S, so let's make a numerical test. Here we have a perfectly conducting circular cylinder. This cylinder is infinite in the perpendicular dimension, so imagine the cylinder is with its axle, cylinder axis is parallel to Z axis, okay, and it is an infinite cylinder, okay, infinite. So in the direction perpendicular to the computer screen, the cylinder is infinite, and it's circular in the XY plane is circular, okay. And this problem has exact solution. We will solve this problem, we will obtain the exact solution for this problem in chapter 4, but it has exact solution. So since it has an exact solution, I can compute for this problem easily the equivalent currents as the tangent components of electric and magnetic fields along surface S, because we know the solution for this problem. We know the electric and magnetic fields that are the solution for this problem. So we compute the equivalent currents, and we compute the field radiated by this current. We add the incident field. The incident field is in fact the plane wave that is we have an incident plane wave on the cylinder, so this is the incident field. We sum the incident field plus the scatter field or field radiated by the equivalent currents, and what we obtain? We obtain this. Here is another view of the same field. The vertical axis is the modulus of the total field, okay? The color is a red scale, so red color is the color scale shows the magnitude of the field, so red color is the maximum magnitude of the field, and dark blue color is 0, okay? So this is the magnitude of the electric field, and we have 0. So here we have 0 field, okay? Inside the cylinder, this is the cylinder, inside the cylinder we have 0 field. Exactly the 0 field that we set in equivalence theorem. And outside surface S we have the total field, and this total field is the incident field due to the incident plane wave plus the scatter field that is reflected backwards. So incident field is progressive, scatter field is regressive because it's reflected, and the sum is a standing wave. You can see here the standing wave, that is incident field. This standing wave is incident field plus a scatter field that is reflected, okay? So you can very clearly see here that the field is really 0 inside the cylinder. The field is 0 inside the cylinder. Only because when we formulated equivalence theorem, here, we set a 0 field inside the cylinder. So this is coherent with Maxwell's equation, and when we compute the field, we really get that 0. After we have seen this numerical verification that shows that the field is truly 0 inside the inside surface S, now I'll show you what happens when we apply the equivalence theorem, the surface equivalence theorem, to perfectly conducting objects, because this is the case that we will solve with numerical methods. Remember that I said before that this was the easy case, and the other case, the case when the object is dielectric or magnetic, not an object with fields different than 0 inside. In this case, we need to set the equivalence theorem both inside and outside the object and link the two problems using the boundary conditions and get a system of equations, and this is much more complicated. So here we will restrict ourselves to the easy case, which is an also very common case because it's the case of antenna radiation, the case of diffraction of perfectly conducting metallic radar targets. It is an important case, but it is also the easiest to solve. So, if the object is perfectly conducting, the fields are 0 inside, the conductivity is infinite. Here, the fields are 0 inside, in the original problem, due to the fact that the object is perfectly conducting. These are the same as the fields that we arbitrarily set to 0 in the equivalent problem. So in this case, the original problem and the equivalent problem both have 0 fields inside, and this simplifies the things a lot. We also have a surface current. You know that we have an incident field. The impressed currents exist in this case only outside the object in volume V, because inside the object, if it is perfectly conducting, we cannot have sources inside. So in this case, the sources exist only outside. They radiate some field that we know the radiation of the impressed currents in free space is the incident field, and this field is reflected or diffracted by the metallic object. And you know that in this case, surface current is induced in the surface of the perfectly conducting object, and the boundary condition gives us the value of the induced current. It is n cross the magnetic field H, or the tangent component of the magnetic field. Remember that, as always, when we have n cross H and we say the tangent component of H, we mean the tangent component rotated 90 degrees, as I said before in chapter 2. Okay, but there is also another boundary condition, that is that the tangent component of the electric field is equal to 0. Okay, now we set the equivalent problem. In the equivalent problem, we set to 0 the fields inside the object. They were already 0, but anyway, we set them to 0 in the equivalent problem. We build the equivalent currents, the equivalent electric current is equal to N cross H at the surface, and this is exactly the same as the induced current here. And then the magnetic equivalent current is minus the tangent component of the electric field, which is equal to 0 due to the boundary condition at the perfectly conducting surface. So in this case, in the equivalent problem, we have essentially the same sources as in the original problem. Look that in the equivalent problem, our sources are the impressed currents, which are the same as in the original problem, because the impressed currents inside the object are 0 in the original problem, and they are removed in the equivalent problem, so it's the same. And outside we have the impressed sources outside, so the same thing. We have an equivalent electric current equal to the induced current, so the sources are the same. And we have a 0 magnetic equivalent current equal to the original problem, because in the original problem you know that the magnetic current is equal to 0. So the sources are exactly the same in the equivalent problem than in the original problem. So you will say, well, what's the difference? What's the use of formulating the equivalent problem if the sources were, we already had the same sources in the original problem? Well, there is a key difference. In the equivalent problem, everywhere we have everywhere free space. We have epsilon 0, mu 0 everywhere. And in the original problem, we only had free space outside, but we had a perfectly conducting object, not free space here. So we compute the radiation of the source. In the equivalent problem, we compute the radiation of all the sources in free space. And the equivalent current is equal to the induced current. So it is as is. I say as is because it's not what happens, what truly happens, but we do as is. The sources in the original problem radiated in free space. But what we are doing, in fact, is computing the radiation of the sources of the equivalent problem in free space, because they truly exist in free space in the equivalent problem. So we often, when we have to compute for example, the radiation so imagine that this object is an antenna, and we compute the radiation of the currents in the antenna. We compute it in free space, and we cannot do that in the original problem. We are, in fact, setting an equivalent problem and computing the radiation of the equivalent sources in free space in the equivalent problem, and it just turns out that the equivalent sources are the same as the original sources, but they're radiated in free space. To clarify this, I have a slide specific for the case of antennas, which is, I think that the case of antennas is a good example, because it's an example that you already know from your courses on telecom engineering and your antenna theory courses. In an antenna, in the original problem, we have some impressed sources that are the feeding of the antenna. This is the antenna feeding, okay? For example, if we feed the antenna with a coaxial cable, I will draw a coaxial cable here. This is a coaxial cable, okay? We have a coaxial cable, and then the coaxial cable, imagine, for example, that there is no volume and there is a direct connection like this. You know that you cannot do that because you need a volume, but anyway, just conceptually, the impressed currents are the equivalent currents at the surface of the coaxial open end, okay? And these currents radiate a field. These currents radiate a field that is the incident field. So in the original problem, the only currents that radiate are the impressed currents that produce the incident field in free space, or the total field, the real field in presence of the antenna. And the shape of the antenna, only the shape of the antenna, this here, only sets a boundary condition. The field of the surface of the antenna sets a boundary condition that modifies the fields that are now different to the fields in free space or incident field. So in the original problem, we have the impressed currents radiated in presence of a perfectly conducting surface that is not free space. We also have, as you know, we also have an induced current, okay, equal to N cross H at the surface. We also have an induced current, but the induced current does not radiate. The induced current here does not radiate. Why? Because the induced current does not radiate in the original problem, I mean. For example, it is easy to understand. We have a perfectly conducting surface, okay? We have an incident field, okay? We have electrons. We have electrons. The incident field accelerates the electrons, so they move harmonically. They move, they have a sinusoidal movement, they have a harmonic movement. And this electron moving is the induced current. But observe that the electrons absorb power from the incident field, and this power is then re-radiated by the induced current, so the total power balance is zero. If we, let's change the color, if we create a surface here around the electrons, if we create a surface here, the power that enters the surface due to the incident field is equal to the power that exits the surface due to the re-radiation of the induced currents. So these induced currents, in fact, only produce, like if it is an infinite plane, these induced currents only re-radiate the incident field, reflect the incident field, but they do not introduce power in the system. The net power crossing a surface that encloses the object is zero. Okay, so they do not introduce power in the system. They just re-radiate power, and adding the radiation of the induced current, which is the scattered field, plus the incident field, we have the total field. So they modify the incident field to produce the total field. This is what happens in the original problem. So in the original problem, we don't have free space, we don't have currents radiating in free space, the induced currents do not radiate, and the impressed currents radiate in presence of the object, not in free space. However, in the equivalent problem, we have everything radiating in free space. We have equivalent currents equal to the induced currents, the impressed currents, they all together radiate in free space, so it is easy to compute. We compute the field due to the impressed currents as the incident field in free space. We compute the field due to the equivalent currents as a scattered field in free space, and then we have to sum both together. Very, very often, for example in a dipole, very, very often, the scattered field is much larger than the incident field. Okay? And we remove the incident field here, and we only compute the radiation of the equivalent current, which is the scattered field. So for that reason, in your antenna theory courses, you have the induced current at the surface of the antenna, and you compute the radiation of the induced current at the surface of the antenna in free space, but what you are doing in fact is computing the equivalent current, the radiation of the equivalent current in free space, because the equivalent current radiates in free space and the induced current in the original problem does not radiate. You compute the radiation of the equivalent current in free space, and you neglect the radiation of the impressed sources because it's very small. In fact, if you use a computer simulation software or your own software, if you write the code, you do compute the radiation of the impressed currents in free space and add it to the radiation of the equivalent currents. Because using a computer, it's easy to compute it and add it. If you have to do the computations analytically, it is much simpler to neglect the terms that are very small. But if you use a computer, you just compute the radiation of impressed currents always, and if it is significant, it will modify the overall result. If it is negligible, it will not modify the overall result. But anyway, using a computer code, you always take into account the radiation of the impressed currents. In your manual and analytic calculations from your antenna theory course says you only compute the scatter field due to the equivalent currents. Okay? And so we can set an integral equation. We will keep here restricted to the easy case, which is perfectly conducting case. In this case, remember, as I said before, we have the total field equal to the incident field due to the impressed currents and the scatter field due to the equivalent currents. The impressed field, the incident field, sometimes it is simply, for example, a plane wave. The incident field can be a plane wave that is incident on a perfectly conducting object. This is a PEC object, okay? And then in this case, oh sorry, not this. In this case, oh no. Well, if we have a current, a plane wave incident on a perfectly conducting object, okay? So this incident plane wave is the field created by the impressed currents, and then we don't care about what the impressed currents are. We just know that the incident field is a plane wave. So there are very two common cases. One, incident plane wave on a perfectly conducting object. Here from the beginning, we set the incident field equal to a plane wave, and we don't care about the impressed currents. Or the antenna case, in which we have to know the feeding of the antenna to compute the impressed currents and the field radiated by the impressed currents in case that it is significant. We can neglect it very often. Okay? And then we have the scatter field due to the equivalent currents. So incident field plus scatter field. The scatter field is the radiation of the equivalent current, so it is the convolution of the Green's function with the equivalent currents. And we can set this for the electric or the magnetic field. In this case, it's for the magnetic field, it's the convolution of the Green's function for magnetic field due to equivalent electric current with the equivalent electric current. Okay. Now these are the radiation equations that gives us the electric and magnetic field, but the problem is that, as you know, the equivalent current is equal to N cross H, so it depends on the magnetic field, and then we cannot directly compute the electric and magnetic field using these equations. What we have to do is to set the boundary conditions. When we set the boundary conditions, we have N cross E equal to 0, so it is N cross incident field plus N cross the convolution. For the magnetic field, the boundary condition is N cross H equal to the induced current, which is the equivalent current. So we have the equivalent current equal to N cross incident field plus N cross the convolution. And now we have two equations, And in these two equations, we know everything except the equivalent electric current, which is the unknown. So we have these very simple equations where we know the incident field, we know the Green's function, and we have an unknown, which is the equivalent current. And we have two equations. The first, for the electric field, is called electric field integral equations. That is EFIE, electric field integral equation. And we have also another equation for the magnetic field, which is called magnetic field integral equation, MFIE. It is interesting to observe that the unknown is only inside the integral in the electric field integral equation, while the unknown is both inside and outside the integral in the magnetic field integral equation. They are integral equations of different kind. The EFI that only have the unknown inside the integral is called a first kind Fredholm integral equation, and the MFI that has the unknown both inside and outside the integral is called a second kind Fredholm integral equation. And they have different behavior. So later, when we have in the chapter on numerical methods, we analyze these two equations, we will see that they have different properties and that they are useful for different cases, and they have advantages and disadvantages. And this is due to the fact that one of them has the unknown also outside the integral and the other doesn't. Okay? Well, and to finish with the surface equivalence theorem, just two alternative formulations. Formulation A is the one that we have already seen, the one in which you have zero fields inside surface S, and you have free space inside surface S, the same as outside, so you have free space everywhere, and you have equivalent currents, the electric equivalent current and a magnetic equivalent current that radiate in free space. So everything radiates in free space. We can do a second formulation, formulation B. Since we have zero fields inside S, while the fields are zero inside S, we can put anything inside S that does not perturb the fact that fields are zero inside S. So we can fill S with a perfect electric conductor. Okay, we fill this with a perfect electric conductor. The fields are still zero inside. What happens? That now the electric and magnetic equivalent currents are the same because the boundary condition is the same. The difference between the fields outside that are E and H and the fields inside that are zero. The equivalent currents are the same, but now the equivalent currents radiate not in free space, but in the presence of a perfect electric conductor. And remember that analyzing the case of antennas, I told you electric current in the surface of a perfect electric conductor does not radiate because the power balance is zero, etc., etc. I remember that I explained you that the electrons at the surface were absorb power to get accelerated, and then they radiated the power, and there was a power balance equal to zero. I told you this before. The electric current in the surface of a perfect electric conductor does not radiate, so we have to remove this. Okay? So what remains is the radiation of a magnetic current in the presence of a perfect electric conductor. We can do the dual case. This is formulation C. The dual case is that we fill surface S not with a perfect electric conductor but with a perfect magnetic conductor. Still, the fields are zero inside because it's dual, but the electric field of the perfect magnetic conductor is equal to the magnetic field of the perfect electric conductor equal to 0. So the fields are still 0. But now, according to duality, the current that does not radiate is the magnetic current, so this current does not radiate, okay? And the current that radiates is the electric current. So we have the electric current radiating in presence of a perfect magnetic conductor. In general, these alternative formulations B and C are not very useful unless surface S is an infinite plane. If surface S is an infinite plane, we can apply image theory. And in image theory, for example, you know, when you compute from your antenna theory courses, you know that when you compute the radiation of an aperture at a ground plane, you have, in fact, initially you have equivalent currents, okay, that are electric and magnetic, okay, initially. And then you feel, this is the volume B outside S, this is surface S, the infinite plane, and inside, this is inside, and this is outside, okay? So here is where you have the fields equal to 0, okay? And this is the aperture. Inside S, since the fields are 0, you can fill inside S with a perfect electric conductor everywhere, inside S, okay? And now you have the radiation of the magnetic current, but also you have the radiation of the equivalent electric current, but the equivalent electric current does not radiate because when we apply image theory, it has is a current parallel to the ground plane, and it has an opposite image. So this is the reason why the electric current in the surface of a perfect electric conductor does not radiate. It is very clearly seen if the perfect electric conductor is a ground plane, is an infinite plane, sorry. If it is an infinite plane, we can see that there is an image current parallel also to the conductor that is located at the surface, at the inside of the surface, and cancels out the current in the outside. So, in the case of an infinite plane, we can clearly see that the equivalent electric current in the surface of a perfect electric conductor does not radiate. And we see this using image theory. If the perfect electric conductor is not an infinite plane, but it has any shape like this, any shape, like this or like this, whatever, it still does not radiate. We can easily see that it does not radiate with an infinite plane, but if it is not an infinite plane, it also doesn't radiate. Okay, so with this we finish chapter 2, the chapter on theorems and principles. Now we have a strong background. We have reviewed what was necessary. We have also introduced new concepts and new things that were new to you. And now we have a strong background that we can use to start with numerical methods in chapter 3.